Hi, welcome to part 2 of lecture 3 of EEE 107. Okay. So in this part of the lecture, we'll be talking about the Hilbert transform and what we call the quadrature filter, which is an important element of uh, communication systems. And after that, we'll be talking about distortion. Okay. So just a review of the previous lecture. We talked about the linearity and time invariance properties of a system, which will be the focus or what we will use for communication systems. And practical communication systems actually use LTI systems, okay, as your blocks. The system responses can offer multiplication uh, and multiplication, differentiation, integration, and so on and so forth. And I've shown you that LTI systems, system responses can be analyzed using convolution, can also analyze them by scaling in the frequency domain by using Fourier transform. We also identify different types of filters, how their responses dictate or deviate rather when implemented in practice, and we also looked at systems as block diagrams. So instead of looking at the physical implementation of a system, we'll look at its behavior only. The output depends on the input. We don't know how it works. We don't care how it works. We just know it works. Okay? And that's how we view communication systems. Right. So now I will introduce to you what we call the quadrature filter. The quadrature filter is an example of an all-pass filter which has the following time and frequency domain properties. Okay? So what does this mean? So you have HQ of t, basically 1 over pi t. This is actually useless. Okay? So it's kind of useless. Okay. So the Fourier transform is what we're looking for. The Fourier transform looks like this. Okay. What does this mean? So basically, if we have a signal x of f, we recall that the output, if we put it in the quadrature filter, will just be a scaled version. But does it scale anything? In terms of magnitude, it does not scale anything. Okay? The magnitude does not scale anything. But the phase actually is different. So for positive frequencies, you observe a 90 degrees phase shift because of this negative j right here. For negative frequencies, you you have a positive 90-degree phase shift because of the positive j right here. Right. And this is what happens when you use a quadrature filter. If you have a signal, so if you have a signal, put it in a quadrature filter, you get a phase shift in your positive and your negative frequencies, different phase shifts actually. So what is its use? So it's used for what we call the Hilbert transform. Given a signal, x of t, its Hilbert transform is taken from convolving the quadrature filter, basically by putting in your x of t in a quadrature filter. The output is actually your Hilbert transform. Okay? So it's in this form, right here. And basically, you perform Hilbert transform if you use the quadrature filter. And it's easier to analyze in the frequency domain, right here. And this is essential when we discuss in-phase and quadrature components of modulated signals. So why is that? Okay, so before we go to the properties, Hilbert transform is used to extract what we call pre-envelopes of real signals. So recall that real signals exhibit Hermitian symmetry. So your magnitude response has an even symmetry and your phase response has an odd symmetry. So that means that when we want to look at the positive response of a circuit right here, we can extract this so-called upper pre-envelope by using the Hilbert transform. Okay? So we can get the upper pre-envelope by adding the original signal plus j times the Hilbert transform. And if you take the difference, then you get the negative or the lower pre-envelope. Okay? And what does this do for us? This actually saves us bandwidth. So instead of occupying the whole frequency response, your signal now just occupies 1/2 of its original bandwidth that it occupies. Okay? So with this, you actually save bandwidth when you try to transmit. And we'll talk about this in a future lesson or a future topic. Okay? So now just some properties of your Hilbert transform. The magnitude response, as I've mentioned earlier, it's the same. It's equal. Okay? If we get the Hilbert transform of the Hilbert transform, we result into a negative uh, of the original signal. So, a question for you. We'll talk about this during the lecture. Why? So, you can try to maybe, I don't know, use this. And you will see. Okay? And your x and x hat of t are orthogonal. What does that mean? If we get this integral of these two, if it's periodic, right? If we get the integral of these two, then that will result into 0. Similarly, if it's a periodic signal, then if we get the integral of this of their product, then you integrate that negative infinity to positive infinity, you'll get also 0. Okay, so the way that I can prove this to you is, why don't we try it on a cosine, cosine function, which is basically 1/2 of e to the j 2 pi ft plus e to the minus j 2 pi ft. Okay? If we apply the Hilbert transform to x of t, then its Hilbert transform is equal to, I'll leave the math to you, but it will look like this. Okay? And this is actually equal to your sine. Now, if you try to integrate your sine with your cosine over one period, you multiply them together, you will actually see that the output of that integration will be 0, making sine and cosine orthogonal to each other. Right? So, this negative 90 degrees phase shift right here, okay, the negative 90 degrees and positive 90 degrees phase shift is actually the same phase shift as doing this, like, and that is equal to your sine carrier or your sine function. So if you put your cosine function in a quadrature filter, it will just become a sine function. Okay? So now recall how signals are a summation of cosine and sine functions. And this is another version of your Fourier transform, or Fourier series rather. So we can decompose a signal to its cosine and sine components. If we put it in a quadrature filter, the resulting output signal will be orthogonal because of the fundamental property of your cosine and your sine signals. Okay? Right, so that's some properties of the Hilbert transform. Okay, now let's talk about signal distortion. So signal distortion is the alteration of the shape of a waveform due to the imperfect response of the system. So if we put this perfect rectangular pulse in your system with an impulse response h of t, because of h of t, let's say because it's so slow, then the signal does not immediately reach its peak. Okay? And when the signal goes off, the signal does not immediately reach its turned off state. And real systems are actually something like this. Okay? Real systems are slow compared to an immediate rise of your signal right here. And this is an example of signal distortion. For example, if we have an RC filter as your system, if the input is a unit step function, right here, the output of your RC or the response of your RC will look something like this. Oops, sorry, Siri.
I didn't catch that.
Oops, yeah, just wait. Okay, there you go. So you have this output response of an RC filter. It looks something like this. There you go. You have some form of a rise time because of your slow RC response. Okay? So distortionless transmission, this is what we want to achieve. Distortionless transmission is when the output has the same quote-unquote shape as the input. Basically, if we have an input here, the output that we desire is maybe something like this, a time-delayed version, still the same shape, and scaled by some factor k, but your output still has the same shape as the input. Okay? So, in mathematical terms, basically you want your output y of t to be equal to k times x of t minus tau. So if your response is delayed, and scaled in amplitude, as long as the shape is the same, then we can say that the transmission is distortionless. And this is when we achieve a perfect communication. Okay? So a perfect communication arises from distortionless transmission. Right? So in the time domain, it looks like this. Okay? An LTI system that does that is a response with something like this, just a delta function that is delayed with respect to time, or an impulse function. That's your impulse response. And the frequency domain looks like this. So basically, the output is equal to this in terms of its frequency response. Okay. So the transfer function basically looks like this. If we decompose it to its magnitude and phase spectrum, the magnitude should be constant. Okay? And then the angle or the phase looks like this. Okay? It's linear with respect to frequency with some phase correction factor. So we have a linear function in the phase, and in the magnitude we have a constant response. Okay? Question is this required for all values of f? Not necessarily, actually. We can have a low-pass filter that is still distortionless. How? In its frequency response, let's say the magnitude response looks like this. Okay? It's still flat in some bandwidth. Okay? And its phase response at that point could be something like this. It's still linear, negative linear, in your phase response. Okay? And this is a distortionless transmission at work. If your signal has a bandwidth B, right, and the response of the system is constant in that bandwidth and a negative linear in its phase response, then you still have achieved distortionless transmission. And a bonus for that, and an added bonus, you have filtered out any unwanted signals outside of your bandwidth. Okay? So basically, for a distortionless transmission, it's not required that this is satisfied for all values of f. So you can just contain it in a certain bandwidth, okay, and you just disregard the other frequency bands. Okay? And that's how distortionless transmission works. Okay? So now there are types of distortion. Linear distortion, if basically your system does not satisfy the distortionless transmission. Okay? So the magnitude response may not be constant over your signal bandwidth. Your phase response may be nonlinear. Okay? So just a caveat, a constant time shift is not the same as a constant phase shift. A constant time shift arises from linear phase response. Okay? The other type of distortion is the nonlinear distortion. The nonlinear distortion is due to the nonlinearities of your system or device. So uh, that would be from your amplifiers, they use BJTs or diodes, right? Nonlinear devices. We can linearize them, but at some point, if your signal is too large, then your system will now be nonlinear. And because of that, we cannot describe your system by a transfer function. Okay? So how do we fix distortion? First, let's look at linear distortion. If we have a channel that is non-ideal, right, introduces distortion, then we can remove the distortion by what we call equalization. Using the process of equalization, we use an equalizer to basically make the total response of the system be equal to this. That's it. So that's how you fix linear distortion. If you have a channel that introduces distortion, then you use an equalizer such that if you multiply their frequency responses, then you get your condition, you satisfy the condition for distortionless transmission. Right? So we can think of equalization as inverting the effect of the channel, sometimes called the channel inversion. Okay. So for example, let's say you have a wireless transmission. You have a transmitter antenna, and it has a signal that has a line of sight, but some parts of the signal will bounce off because of the ground, and another form of the signal arises. So this is a simplified version of a wireless communication system because of multiple propagation paths. Well, let's say that just has one reflection. And this is actually true for long-distance communication systems. Okay, now the output of this system is equal to this. This is from your line of sight signal, and this is from your ground reflection. Okay. Some note that this K2 right here is less than K1. Why? Because the signal needed to travel in a longer distance just to get to the receiver, and the time it arrived is, well, it's greater than the time of arrival of the first signal. Okay, so this is the response based on the behavior of the channel. Okay, so we need to solve for the frequency response of the channel, and that is by getting the ratio of the frequency response of the output divided by the frequency response of the input. By using the properties of Fourier transform, a time delay is, well, basically just something like this. Okay, and then you get the channel response. It's equal to this. So we factor out this one. Okay, and we result into this equation inside and sum of this equation inside. Just let k be equal to k2 over k1, and this delta t is the time difference between the two signals, time difference of arrival between two signals. It's t2 minus t1. And the equalizer, well, we want the when we multiply the equalizer frequency response with the uh, h of f right here with the channel response, we want it to be this function right here, and it's equal to this. K here can be arbitrary. K and T1 is arbitrary. So the most efficient way to, the most efficient is equal to this. Okay? And we can now solve for the equalizer. So the equalizer is equal to this function right here. And this can be, this equalizer can be physically realized. Okay? So now let's look at a nonlinear system. So the nonlinear system can be, well, generally we can define the input and the output transfer characteristic by this equation right here. A nonlinear transfer function will can be approximated as a polynomial expression, something like this. Now, where did this come from? Well, if you have already taken advanced calculus, this comes from the Taylor series. Okay? So, generally, the transfer function of a nonlinear system has powers of the signal. Okay? And if we get the frequency response of that, we have a lot of convolution right here. Now, if the system is linear, then this is 0, this is 0, and this is 0. Okay? And so is this. But since it's nonlinear, it's present in the system. Okay? And this typically occurs in electronic devices with nonlinear elements. Your diode is defined by your exponential function. Your MOS is defined by the square law, and so on and so forth. If the bandwidth x of t is equal to some b, then the bandwidth of the transfer function is equal to k times b, where k is the highest power. So the nonlinear system distorts the frequency response, okay, and increases the bandwidth of the output signal. And of course, we want to save bandwidth, so a nonlinear system does not really help. Okay? So an example would be a clipper. So a nonlinear distortion will clip off the signal, and I hope you have observed this in your EEE 52, your electronics lab. When the signal is too large, the input signal is too large, the output signal will have some form of clipping at the top and the bottom. Okay? And this clipping introduces harmonic components, which is, well, basically what happens here. Okay? And how do we fix it? We can't really fix it in the same way as linear distortion, but we can avoid it. Okay? So if the problem is, if the signal is just too large, then maybe we just need to compress it. And then if we compress it at the transmitter, and then at the output, we have to expand it. This is the process we call companding. Okay? You compress the signal at the transmitter, okay, and expand it at the receiver. So we have a nonlinear system here at the input where we compress the signal, okay, pass it through the channel that is not forgiving, and then expand it at the output. Okay? So the expander at the receiver must negate the effects of this compression. Okay? So now, if it passes through the channel, instead of clipping off, we control this distortion by it won't be clipped off. And we reverse the process, we get the original signal. We get at least close to the original signal, right? So that's how we fix the nonlinear distortion. I'll give you a demonstration of that when we meet during the lecture. Okay, so this is an example of companding using MATLAB. So I'll also give you the simulation files, so don't worry about that. So if you cannot attend class, you can just try to play with the simulation files. Okay, so that's the end of this presentation, the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Okay. So thank you for listening. See you next meeting.